Okay, so for anyone who's ever, dipped a toe into quantum physics,
Yeah.
you hear these terms, superposition, entanglement, and it just often leaves you scratching your head.
Oh, absolutely. More questions than answers sometimes.
Exactly. So today, we want to go beyond just the headlines. We're aiming to really get under the hood, understand the fundamental reality that shapes, well, everything, and powers the tech of tomorrow.
Mm-hmm.
Because this stuff, it isn't just abstract science anymore, is it? It's the bedrock, the foundation for tech that's going to fundamentally reshape your future.
That is absolutely the mission for this deep dive. We want to unpack those really mind-bending insights.
Yeah.
And we're leaning on some brilliant minds here, folks, like physicist Brian Cox and, of course, the legendary Richard Feynman. His lectures, still gold standard for clarity on quantum mechanics.
Absolutely legendary.
Our goal is to take that quantum weirdness and make it understandable, make it relevant to you.
Right.
Because, look, understanding these core ideas isn't just, theoretical curiosity these days. With quantum tech taking off, especially things like quantum computing, this knowledge is becoming practically essential. It's moving way beyond just the world of atoms.
Okay, so let's dive right in then. A common idea, maybe a misconception, is that quantum means different rules for tiny things.
Right, like a totally separate rule book.
Yeah, like there's one set of physics for, I don't know, baseballs and planets, and another completely alien set for electrons. But Brian Cox, who we're drawing on quite a bit today, he pushes back hard against that. He says, and I think this is key, there aren't different rules of the game in the subatomic world and the world that we observe.
That's such a crucial point.
So what does that actually mean for us? It means our everyday common sense world, the one we see and touch, it actually emerges from these, yes, strange, but very precise quantum behaviors.
That's all one system.
It's all one system. The rules just manifest differently depending on the scale you're looking at.
And what's so fascinating now is how that perspective, it's shifted from just being a philosophical point, something academics debate,
right.
to being a practical imperative. Quantum phenomena are absolutely not just for abstract discussions anymore.
Okay.
We're seeing more and more quantum technologies, real devices being developed that directly use these behaviors. Quantum computers are, well, the poster child for this.
Right, the big one everyone talks about.
Exactly. So understanding this stuff isn't just for the physicists in labs. It's practically important because we're starting to harness these quantum effects in the real world. You need to grasp it to understand the tech landscape that's coming.
That makes sense. And, understanding this shift, it sometimes helps to look back at how we even got here, how we figured this stuff out.
The history, yeah.
Brian Cox talks about his own experience back in university in the 90s. He describes how quantum mechanics was often taught chronologically.
Tracing the steps.
Yeah, you'd start with the early experiments, maybe the photoelectric effect, then Rutherford finding the nucleus, Bohr's model with electrons in orbits.
The historical breadcrumbs.
Right. And while that shows how science progresses, Cox argues it kind of inadvertently transferred decades of the initial confusion, the real intellectual struggles the pioneers had, straight to the students.
That's interesting, like inheriting the confusion.
Exactly. Because it was a crisis for physicists back then, trying to make sense of observations that just flew in the face of everything they thought they knew.
So this brings up a really important question then. Why the big shift in teaching it now?
Good question.
Well, most universities today, they largely start directly with the established theory, the way we understand it now.
Ah, okay. So start with the current picture.
Pretty much. They present the current model for how the world fundamentally works. It prioritizes clarity, understanding the paradigm we have today, rather than making students relive all those historical battles and uncertainties.
Makes sense. More direct.
Much more direct, yeah. More efficient, and really focuses you on the implications of what we've actually discovered.
Okay, so to really get a feel for how different this is from our, everyday intuition, let's unpack a couple of core concepts.
Let's do it.
First one, spin and qubits. Now, we all get a classical coin, right? Flip it, it's tails. Done. One state or the other.
Clear cut.
Now, imagine a quantum coin. We call it a qubit, this thing. It can be in what's called a superposition, which means it's not just heads or tails. It can be a mixture of both at the same time, like maybe 30% heads and 70% tails, potentially, or any other mix, until you look, until you measure it.
So it's fuzzy until you measure it.
Kind of.
Yeah.
A real example is electron spin. Classically, you might think up or down. Quantum mechanically, it can be in a superposition of both up and down simultaneously.
Right. And if we connect that idea, that superposition, to the bigger picture, It really changes how we think about probability itself. Well, in classical physics, right? If we say there's a 50% chance of rain, that's usually because we just don't have all the information.
Like, we don't know where every single water molecule is.
Exactly. Probability, in that sense, reflects our ignorance, our incomplete knowledge.
Okay.
But in quantum theory, these probabilities, they seem to be fundamental, baked into nature itself.
Whoa, okay. Not just us not knowing enough.
Precisely. They are intrinsic to how the universe works. They don't just pop up because we lack data about the system's exact state. Brian Cox nails this. He says, pretty much all of the intellectual challenges and the confusion around quantum mechanics comes from that very simple property.
The probability is fundamental.
Yes. It's not just missing information. It's a basic, irreducible unpredictability at the very heart of reality.
Well, it's a huge shift from thinking the universe is just a super complex clockwork we haven't fully mapped out yet.
Yeah, it implies it's inherently probabilistic.
It's a radical shift. Okay. And for anyone still trying to, like, visualize this weirdness, the double-slit experiment, that's the classic, right?
Yeah.
It packs almost everything confusing about quantum mechanics into one setup.
It really is the cornerstone. If you want the absolute best description, Richard Feynman's take in the Feynman Lectures, Volume 3, Chapter 1, it's unbeatable.
Highly recommended.
Yeah.
So the setup, probably familiar to some listeners, but let's recap. Simple enough. You have an electron gun shooting electrons,
Okay.
a barrier with two narrow slits in it, and then a detector screen behind that to see where the electrons land.
Got it.
Now, if electrons were just tiny bullets, like little ball bearings, what would you expect to see on the screen?
Well, you'd expect two distinct bands, right? Just piles of hits right behind each slit.
Exactly. Two lines. Simple.
Yeah. That is absolutely not what happens.
No. What do we see?
You get an interference pattern, a whole series of bright and dark stripes spread across the screen, just like you'd get if you sent waves, like light waves or water waves, through two slits.
Waves interfering with each other. But these are electrons. We thought they were particles.
Exactly. And here's the really profound part. You still get this interference pattern even if you send the electrons through one at a time.
Okay, wait. One at a time. How can one electron interfere with anything?
Well, that's the deep mystery. It implies that each single electron, somehow, it explores both paths through the slits simultaneously.
Both paths at once.
And then it interferes with itself before it lands on the screen.
Interferes with itself.
Yeah. And Cox points out, some people might hedge and say it's as if it does this, but many physicists today, they just say, no, it does. It goes through both paths.
That just completely breaks our classical idea of particle following one definite path from A to B.
Completely. It shatters it.
Okay, now, Feynman's way of calculating this is where it gets even more interesting, maybe even weirder.
His calculational prescription, yeah, it's brilliant and strange.
He explains that to figure out the probability of an electron landing at any specific spot on the screen, you have to assign a complex number to every possible route the electron could take.
Every route, like literally any path.
Every conceivable path, from the gun through the slits to that point on the screen. He visualizes these complex numbers as little spinning arrows, or clock faces. They have a length and a direction, an amplitude and a phase.
Okay, these little clock hands for every path.
Right. Then for any point on the screen, you add up all those little claw hands, all the complex numbers for every single path leading there.
Add them all up. Vector addition, essentially.
Exactly. And the final probability of finding the electron at that spot. It's the squared length of the final combined clock hand you get after adding them all up.
Wow. Okay. That's a procedure, but what does it mean?
That's the million-dollar question. And it leads straight into this deep philosophical and physical debate about interpretation.
Right. Is it just a calculation trick that happens to work? A mathematical tool?
Or does it mean the electron literally explores every possible route?
And when you say every route, you mean every route, like going to the Andromeda Galaxy and back on its way to the screen.
Theoretically, yes. The calculation includes all paths. Now, that debate is definitely ongoing. But many physicists today are increasingly leaning towards the idea that this mathematical picture is reality, that particles genuinely behave this way.
That is deeply weird. It really forces you to rethink what reality even means at that level, doesn't it?
It absolutely does. It's like the universe is constantly calculating probabilities using these, well, almost imaginary paths. And this isn't just some theoretical curiosity anymore.
Right, this path integral idea, this weirdness, it's actually the foundation for what's coming next.
Exactly. Which brings us neatly to quantum technologies, and the big one, quantum computers.
built using those qubits we mentioned earlier.
Right, leveraging superposition, but also another crucial quantum property.
Entanglement.
Entanglement. Einstein's spooky action at a distance. That's the one. Explain that for us. What is entanglement?
Okay, so entanglement is when you link two or more qubits together in a special way. Their fates become fundamentally intertwined.
Intertwined how?
So intertwined that if you measure the state of one qubit, say, you find out its spin is up, you instantly know the state of the other one, no matter how far apart they are.
Instantly.
Okay.
Even if one is here and the other is across the galaxy.
In theory, yes, instantly. That's the spooky part that bothered Einstein, Podolsky, and Rosen the EPR paradox guys.
Okay, can you give a quick example?
Sure. Think of a simple entangled state of two electrons called a Bell state. It might be described as something like up, down, plus down, up.
Meaning?
It means the pair is in a superposition. If you measure the first electron and find its spin is up, the state collapses, and you know instantly, guaranteed, that the second electron's spin must be down.
And vice versa.
And vice versa. It's not just that you gained information. It seems like the system itself instantly settles into that configuration across space.
And we know this happens. It's not just theory.
Oh, yeah. Experiments, incredibly precise ones, the kind that won the Nobel Prize a few years back, have basically slammed the door on loopholes like hidden variables that might have predetermined the results. This seems to be just the way the system is.
Wow, okay.
Yeah.
Spooky indeed.
And that property, entanglement, combined with superposition, is what gives quantum computers their absolutely staggering potential power.
How does that work? How does entanglement lead to power?
Think about the number of states. One qubit can be 0 or 1 or a mix. Two qubits can be 0, 0, 0, 0, 1, 10, or 11, 4 possibilities, or superpositions of them. Three qubits, 8 possibilities.
Oh, and it's doubling each time.
Exactly. The number of configurations for n entangled qubits grows exponentially. It's 2 to the power of n.
2 to the power of n that gets big fast.
Unbelievably fast. Get this. With a relatively small number of qubits, maybe just say 100, or even up to maybe 500, the number of possible states they can represent simultaneously.
Yeah.
It can actually exceed the number of atoms in the entire observable universe.
Okay, that's hard to even comprehend. The number of states is bigger than the number of atoms in the universe.
Yeah.
With just a few hundred qubits.
Mind-boggling, isn't it?
So what does this actually mean? Why is this exponential power so important?
Well, this immense configurational space, this ability to represent and process information on such a massive scale simultaneously, that's what quantum computers aim to harness.
Right.
That's why you see the tech giants, Google, Microsoft, IBM, and many others pouring billions into building these devices.
Because they can do things classical computers just can't.
Exactly. They have the potential to perform calculations that no conceivable classical computer, not even a supercomputer the size of a planet, could ever complete within the lifetime of the universe.
Wow. Like what kind of calculations?
Think about designing new drugs or materials. You'd need to simulate how complex molecules interact. Classically, that's incredibly hard. A quantum computer could potentially explore all the possibilities at once.
Or optimization problems.
Huge optimization problems, yeah. Logistics, finance, breaking complex codes, training AI. The list goes on. This ability to navigate this vast computational space is what could revolutionize problem solving.
So it feels like we've covered a lot of ground here in this deep dive. We started with this idea that quantum physics isn't separate rules, it's the fundamental reality.
The foundation from which our world emerges.
We saw how our understanding, even how we teach it, evolved from that initial understandable confusion to a clearer, more direct approach.
Focusing on the current paradigm.
Then we unpacked some of those really counterintuitive ideas, superposition, the quantum coin being heads and tails.
Right, and fundamental probability, not just ignorance.
Yeah, that was a big one. And the double-slit experiment, showing particles taking all paths.
The quintessential quantum weirdness.
And finally, entanglement, that spooky action linking quantum fates across distance.
Which enables the power of quantum computing.
And all this weirdness, this fundamental truth, it's now being actively harnessed. Built into these potentially world-changing quantum computers. It really underscores why understanding this stuff is becoming so important for your future.
It really does. And maybe here's a final thought to leave you with, something to chew on.
Good.
If probability really is fundamental to nature, if particles genuinely do explore all possible paths, even the seemingly absurd ones, what does that really imply? What does it say about concepts like destiny or chance, or even our basic understanding of certainty in the universe?
Hmm. That's a deep one. Does it mean everything is just probabilities all the way down?
It's a question that physics and philosophy are still grappling with. It challenges some of our deepest assumptions about reality.
It certainly does. Definitely something to think about. And hey, if you want to dig deeper, especially into that double-slit experiment, seriously, track down Feynman's lectures, Volume 3, Chapter 1.
A must read.
Truly eye-opening. We really hope this deep dive sparked some aha moments, or at least some new questions for you. Keep that curiosity going.
Absolutely.
We'll be back for another deep dive soon. Thanks for joining us.